We begin at the edge of everything. As we float in this quiet, vast expanse, our minds naturally drift toward the ultimate question, the one that sits at the very foundation of reality. We look out at the tapestry of galaxies, each a pinprick of light representing billions of stars, and we trace their stories backward. We see them rushing away from each other, an expansion that rewinds and rewinds and rewinds all the way back to a single explosive moment of creation. And then, standing at that absolute boundary, we ask the impossible question, what existed before the Big Bang? It feels like the most natural question in the world. Our entire lives are governed by cause and effect, by a before and an after. There was a before you started listening to this, a before the Earth was formed, a before our sun ignited. Surely there must have been a before the universe itself. But here at the boundary of beginnings, our intuition may be misleading us. The question itself might be based on a flawed assumption. Think of it this way. If you are standing exactly at the North Pole, which way is north? The question is meaningless. There is no direction called north from the North Pole. Every direction you point is south. The concept of north simply ceases to exist at that precise location. This analogy, famously used by minds like Stephen Hawking, is perhaps the best way to understand the Big Bang. We are accustomed to thinking of the Big Bang as an explosion in a pre-existing dark, empty space. We imagine a void and then bang, a fireball appears in the middle of it. This is incorrect. The Big Bang was not an explosion in space. It was the beginning of space. It was also the beginning of time. Time and space are not a stage on which the universe performs. They are the universe. They are woven together into a single fabric called space-time, and this fabric came into existence at the Big Bang. Before this moment, the concept of time did not exist. Therefore, the very word before becomes meaningless, just as north becomes meaningless at the North Pole. There was no before the Big Bang because there was no time for a before to happen in. The universe didn't start in a moment. It is the unfolding of moments, and this was the very first one. The universe is not just everything that is. It is everything that was and will be. Time itself is a property of the cosmos, and at this boundary it began. So we cannot ask before, but what can we ask? We can ask what happened at the beginning. What was the universe like at the very first instant we can measure? To answer this, we turn to our most powerful tool for understanding the cosmos on its grandest scale, Albert Einstein's theory of general relativity. This is the theory that describes gravity, the bending of space, the expansion of the universe, and the behavior of black holes. It is one of the most successful theories in human history. We can use its equations to run the clock backward, to rewind the cosmic expansion, pushing all the galaxies, all the stars, all the matter, and all the energy back together. As we get closer and closer to the beginning, the universe gets hotter and denser. Everything we see spread across billions of light years is compressed into a region the size of a galaxy, then a star, then a solar system, then a marble. We keep pushing. But then at the very instant of creation, at the point we call T0 or time zero, Einstein's beautiful equations break. They stop making sense. They scream at us. At this time zero, the equations of general relativity tell us that the entire observable universe, all its matter and energy, was crushed into a point with zero volume. This means it would have infinite density and infinite temperature. In physics, when your calculations return a value of infinity, it is not an answer. It is a mathematical red flag. It is the universe's polite way of telling you that your theory is wrong. It means the tool we are using, general relativity, is no longer the right tool for the job. It has been pushed beyond its limits and has collapsed. This point of infinite density and zero size is what we call the singularity. It is the mathematical wall our theories crash into. So what is this wall? What is this singularity that our science points to? Is it a true boundary of reality? Is it the literal point from which everything emerged? A place where the laws of physics as we know them truly did not exist? Is it a hard, impenetrable barrier, an absolute beginning beyond which no questions can be asked and no answers can be found? Is it in essence the end of the line for human comprehension? Or perhaps it is something else. Perhaps this singularity is not a real physical wall at all. Perhaps it is merely a veil. Perhaps it is not the limit of reality, but only the limit of our current understanding. We know our theories are incomplete. General relativity describes the very large gravity galaxies, while quantum mechanics describes the very small atoms, particles. At the Big Bang, the entire universe was very large, but it was also very small. To understand it, we need a single theory that can merge both a theory of everything or quantum gravity, which we do not yet have. This singularity, this wall of infinities, might just be the place where our old map ends. It is the curtain behind which a deeper, stranger and more elegant truth lies hidden. Perhaps the beginning wasn't an infinitely hot, dense point. Perhaps it was a bounce from a previous universe that collapsed. Perhaps it was a ripple in a higher dimension, or something so profoundly different from our experience that we have not yet even developed the language to describe it. This boundary is not a final answer. It is an invitation. It is the frontier where our knowledge stops and our wonder truly begins. That veil at the beginning of time is the great challenge of modern physics. If the singularity we discussed is not a true beginning but just the edge of our old maps, then we must ask, what lies beyond? What do our new, more daring maps suggest? This is where our journey takes a turn away from a single absolute origin and toward a much stranger, more profound idea that our Big Bang may not have been a beginning at all. Instead, it might have been a transition, a moment of transformation like water freezing into ice, or a caterpillar emerging as a butterfly. Our universe may be just one phase, one chapter in a story that is vastly older, larger, and more magnificent than we can comprehend. Let's explore one of these new maps. It paints a picture of a universe that is truly eternal, not one with a beginning or an end, but one that lives in an endless cycle of birth, death, and rebirth. This is the idea of a cyclic universe. We know our universe is currently expanding and it may continue to do so forever. But what if it doesn't? What if billions or trillions of years from now, the collective pull of gravity from all the dark matter and all the galaxies becomes strong enough to halt this expansion? What if gravity begins to win? Imagine that cosmic tide turning. The galaxies would first slow, then stop, and then begin rushing toward each other. This would be a big crunch, the reverse of the Big Bang. As the universe contracted, it would grow hotter and denser, undoing all of its history. Stars would be ripped apart, galaxies would merge, and eventually all matter and energy would be compressed back into an infinitesimally small, hot, dense state, crashing back into a singularity. This was the old idea, but what if that crash could be avoided? This is where our new physics steps in. Some theories suggest that as the universe gets incredibly dense, a new kind of push from quantum mechanics, a force that resists being compressed too tightly, would take over. It would stop the collapse. The universe wouldn't crash into a singularity, it would bounce. This big bounce would be a moment of near infinite density, but not infinite. The universe, having compressed to a mind-boggling degree, would rebound, exploding outward in a new Big Bang, creating a new universe with new stars, new galaxies, and perhaps new life. In this model, the answer to what came before the Big Bang is simple: the universe that existed before this one. Our universe is just the latest breath in a cosmic lung that has been inhaling and exhaling for eternity. There is no beginning. There is only the rhythm of a timeless cosmic heart. Now let's look at a different map, one that is perhaps even more staggering. This map comes from our best theory of the Big Bang, called cosmic inflation. This theory suggests that in the very first fraction of a second of its existence, our universe underwent a period of hyper-fast exponential expansion, growing from smaller than an atom to the size of a grapefruit almost instantly. This theory is incredibly successful. It explains why the universe is so big, so uniform, and so flat. But it has a radical consequence. According to this theory, the inflation that started our universe may not be a one-time event. It might be the default state of reality. Imagine a vast, infinite ocean of cosmic energy, a metaverse that is always inflating, always expanding at this furious rate. Here and there in this chaotic ocean, tiny patches of this energy can suddenly cool down, stop inflating, and form a stable universe. Our Big Bang then was not the beginning. It was just the moment our particular pocket, our bubble, formed in this eternally churning ocean. This is the multiverse. In this picture, our universe is just one bubble in an infinite bubbling foam of other universes. Other bubbles are likely forming right now, far beyond our ability to see, each one starting with its own Big Bang. And these other universes could be profoundly different from our own. The fundamental laws of physics, the strength of gravity, the charge of an electron. The very particles that make up reality might be different in each bubble. Most of these universes would be sterile, dead, collapsing in an instant, or expanding too fast for stars to ever form. But with an infinite number of bubbles, it is inevitable that some, purely by chance, would have just the right conditions for complexity, for stars, for planets, and for life. We are simply living in one of the bubbles that got it right. Our beginning was just the beginning of our home one island in an infinite cosmic archipelago. Finally, there is the most mind-bending idea of all. It is the map that tries to explain how you can get a universe from quite literally nothing. But in physics, nothing is not what we think it is. The nothing of a pre-universe, the quantum vacuum, is not an empty silent void. It is a roiling, chaotic sea of potential, a quantum foam. Governed by the laws of quantum mechanics, this foam is a place where energy and particles are constantly flashing into and out of existence for impossibly short moments before disappearing again. It is a seething cauldron of virtual reality. The laws of quantum mechanics state that what can happen will happen given enough time. In this timeless, spaceless state of quantum foam, tiny fluctuations of energy would appear and vanish. But what if purely by chance a fluctuation was big enough? What if a bubble of energy borrowed just enough from the vacuum, a quantum fluctuation, that it was able to take on a life of its own? According to these theories, a tiny patch of this foam through a random quantum leap could have fluctuated into existence with the exact properties needed to ignite and critically to inflate. The positive energy of all the matter in the universe would be perfectly balanced by the negative energy of gravity, creating a universe with a total net energy of 0. It is the ultimate free lunch. The universe in this view is a something that emerged from nothing, not a void, but a nothing that was pregnant with all possibility. The Big Bang was simply the moment a random quantum possibility became our physical reality. To truly understand what happened at the moment of creation, we have run into a colossal problem, a deep conflict at the heart of physics. For the last century, we have explained our universe using two separate rule books. One is Einstein's General Relativity, the rulebook for the very large. It describes gravity, the graceful bending of space-time, the dance of planets, and the expansion of the entire cosmos. It works perfectly. The second is quantum mechanics, the rulebook for the very small. It describes the bizarre probabilistic world of atoms, electrons, and photons. It is the foundation of our entire technological world, from smartphones to lasers. It also works perfectly. The trouble is, these two rulebooks are not compatible. They are written in different languages. General relativity gives us a smooth-flowing, predictable space-time. Quantum mechanics gives us a jittery, uncertain world of discrete packets of energy. In our everyday universe, this is fine. They stay in their own domains. But the Big Bang is the one place in all of history where the two realms collided. At that moment, the entire universe, an object of ultimate largeness, was crushed into a space of ultimate smallness. To understand that moment, we need a single unified theory. We need the master rulebook that explains them both. This is the search for quantum gravity. We don't have it yet, but we have two extraordinary candidates. The first is called string theory. It is a radical and beautiful idea. It asks you to forget everything you know about fundamental particles. We are taught that if you zoom in on a piece of matter, you find atoms, then electrons and a nucleus, then protons and neutrons, and finally inside those tiny points called quarks. String theory says this is wrong. If you could zoom in even further past the quark, you would find that it is not a point at all. It is a minuscule one-dimensional filament of energy, a tiny vibrating string. Everything in the universe, according to this theory, is made of these tiny strings. And just as a single violin string can play many different notes by vibrating in different patterns, these fundamental strings create all the different particles we see. A string vibrating in one pattern appears to us as an electron. A different vibration makes it a photon. Another, a quark. And most importantly, one specific vibration would create the graviton, the long sought-after particle that carries the force of gravity. In this one elegant idea, all of matter and all of the forces of nature become unified, just different notes in a grand cosmic symphony. How does this help us with the Big Bang string theory? Doesn't just add strings, it adds dimensions. It requires that our universe has many more hidden dimensions of space, perhaps as many as 10 or 11 in total, all curled up so small we can never see them. In this vast higher dimensional reality, our entire universe with its 3 dimensions of space and one of time might exist as a vast sheet-like object which physicists call a brane, short for membrane, but we might not be the only one. String theory allows for many branes floating in this larger space like pages in a book. This leads to a startling new origin story. Our Big Bang may not have been a singularity, a point of infinite density. Instead, it could have been a collision. Two of these giant parallel brain universes may have drifted through this higher dimension and crashed into each other. The colossal, unimaginable kinetic energy from this cosmic impact would have been transformed, releasing a fireball of energy and matter onto our brain. That fireball was our Big Bang, the moment that set our universe expanding and cooling into the cosmos we see today. The beginning was not a mysterious infinite point, but a finite physical and profoundly violent event. Our second major candidate, loop quantum gravity, takes a completely different path. It doesn't start by adding strings or dimensions. It starts by taking Einstein's theory of gravity and merging it dissolutably with the rules of quantum mechanics. It quantizes space-time itself. What does this mean? Quantum mechanics tells us that things come in quanta discrete individual packets. You can have one photon of light or two, but you cannot have half a photon. Loop quantum gravity suggests that space and time are the same way. We experience space as smooth and continuous, but this theory says that if you could zoom down to the smallest possible scale, a distance called the Planck length, a length so small that if an atom were the size of the known universe, the Planck length would be the size of a tree, you would see that space is not smooth. You would see that it is made of indivisible atoms of space-tiny loops or quanta of volume. Space itself is granular like a digital image on a screen. You cannot have a distance smaller than 1 pixel of space. This one idea completely solves the singularity problem. If space is made of these indivisible units, you can never crush the universe down to a point of zero volume. It is physically impossible. The smallest you can make it is 1 atom of space. So what happened at our beginning? In this model, the Big Bang was not a beginning at all. It was a big bounce. This theory suggests there was a previous universe, one that existed before ours. That universe expanded just like ours, but eventually its gravity pulled it back together. It collapsed in a big crunch. But it did not crash into a singularity. It couldn't. It compressed and compressed until it hit that fundamental maximum density that the atoms of space would allow. And then, with nowhere else to go, it rebounded. Violently. That rebound, that explosive expansion from a pre-existing compressed state, is what we call our Big Bang. Our universe was born from the ashes of the one that came before. So we have these incredible competing ideas. A cosmic symphony of vibrating strings, a crash between parallel universes, a granular pixelated space-time, a universe bouncing back from a previous one. But are these just stories, or are they science? To be science, they must make predictions we can test. We cannot build a time machine and go back, but the universe has left us a message. It left an afterglow. This is the cosmic microwave background, the CMB, the oldest light in the cosmos, a faint, all-pervading bath of radiation that comes from a time when the universe was just 380,000 years old. This light is the fingerprint of the infant universe. Scientists are scouring this map looking for clues. If the Big Bounce is correct, the collapse of a previous universe might have left a scar on our own, some large-scale anomaly or pattern in the CMB. If the brain collision model is right, that violent impact would have sent out unique ripples in space-time gravitational waves that would have imprinted a specific twist or polarization in that ancient light. The search is on. We are listening to the faintest whispers from the dawn of time, searching for the one clue that will finally tell us which rulebook is right and what really happened at the boundary of beginnings. We have journeyed from the edge of time to the birth of parallel worlds, from vibrating strings to bouncing universes. We have pushed our theories to their absolute breaking point, to that wall of infinities where our math fails and our imagination must take over. And now we stand at that boundary, the frontier of the great unknown. When we ask these questions, what started it all, or why are we here? We are no longer just in the realm of physics. We are standing in the domain of philosophy, of metaphysics, and for many of God. Where does a creator or a divine belief fit into this picture of a 13.8 billion-year-old cosmos, a universe born from a quantum fluctuation or a collision of brains? This is often seen as a battleground, a place where science and faith must fight. But perhaps we are just looking at it in the wrong way. For some, the vast impersonal and ancient nature of the cosmos is a source of existential dread, making us feel small and meaningless. For others, this very same scale, the mathematical elegance of the laws, the improbable fine-tuning that allowed for our existence, is the most profound evidence of a divine hand, a mind of unimaginable intelligence and subtlety. The story of creation in this light is not a story that ended 13.8 billion years ago. It is a story that is still being told in every expanding galaxy and in our own consciousness. To navigate this, we must be very clear about what science is. Science is not a collection of beliefs. It is a process. It is a framework for observation, a rigorous method for asking questions and testing answers against reality. It is a commitment to following the evidence wherever it may lead and to being willing to change our minds when new evidence appears. The age of the universe, 13.8 billion years, is not a belief or an opinion. It is a measurement. It is a conclusion drawn from decades of independent, verifiable and overwhelming evidence, from the speed at which galaxies are flying apart from the leftover heat of the Big Bang, the cosmic microwave background, and from the life cycles of the oldest stars. It is the most honest answer we have based on the data the universe itself has given us. The real power of science. The thing that makes it so trustworthy is not in what it knows. It is in its honesty about what it doesn't know. This is the frontier. Science is not afraid to say, "I don't know." In fact, it celebrates it. The singularity we discussed earlier is the most honest statement in all of physics. It is the point where we admit our current rulebook fails. We have not answered the ultimate question. We have simply found the edge of our knowledge. And it is at this edge that the most exciting work begins. This brings us to the most profound question of all, a question that science may never be able to answer. It is the question that philosophers and theologians have wrestled with for millennia. Why is there something rather than nothing? Science is getting incredibly good at answering the how. How did the universe expand and cool? How did elements form? How did stars and planets come together? The theories we've explored, like string theory or loop quantum gravity, are our boldest attempts to answer the what. What are the fundamental rules? What happened at the first instant? But the question of why is different. Why do these rules exist? Why is there a quantum foam to fluctuate in the first place? Why is there any reality at all? This why may be the permanent protected territory of philosophy and spiritual contemplation. Science can describe the rulebook of the universe, but it may never be able to explain why that rulebook exists, or who, if anyone, wrote it. This is not a failure of science, it is recognition of its boundaries. The wonder that science reveals does not and should not eliminate mystery or awe. It defines it, it refines it, it takes a vague, unformed sense of wonder and gives it a structure that is more magnificent than any ancient myth. To know that you are made of stardust, that the iron in your blood and the calcium in your bones were forged in the heart of an exploding star billions of years ago, is not a cold, sterile fact. It is a poetic, deeply moving and spiritual truth. It is a fact that connects us directly to the cosmos. Science does not make the world less magical. It reveals it to be more magical than we ever could have dreamed. It gives us a new sense of reverence. The discovery of a universe governed by laws does not remove the space for philosophy or personal faith. It simply provides the most accurate canvas we have, the most honest depiction of the stage on which our lives are set. It creates a vast open space for us to explore meaning, to contemplate our purpose and to grapple with the mystery of our own consciousness. Science, philosophy and spirituality do not have to be enemies. They can be partners. Science builds the house describing the physical reality we inhabit. Philosophy and spirituality are what allow us to live in that house, to furnish it with meaning, and to call it a home. The great unknown is not a void to be feared. It is the space where all of these essential human endeavours can meet. In recent years, our telescopes have confirmed that planets are not rare. They are the rule. It seems that nearly every star has planets. And based on our current data, we estimate there could be as many as 40 billion Earth-sized planets orbiting in the habitable zone of their stars just in our galaxy alone. This is the Goldilocks zone, not too hot and not too cold, where liquid water, the key ingredient for life as we know it, could exist on the surface. 40 billion. And that's just our backyard. This is where a simple, logical and profoundly disturbing question emerges. It was first asked over lunch by the great physicist Enrico Fermi. He considered these numbers, considered the age of our galaxy, and asked a question that now bears his name, the Fermi paradox. If our galaxy is so old, and the ingredients for life are so common, and there have been billions of years for life to arise, evolve and develop intelligence, then where is everybody? This is the tension at the heart of our search for life. On one hand, we have an equation, the Drake equation, which is a famous framework for estimating the number of intelligent communicating civilizations in our galaxy. When you plug in even the most conservative, pessimistic numbers for each variable, The rate of star formation, the fraction of planets that are habitable, the chance of life arising, the chance of it becoming intelligent. The math almost always says yes. The equation tells us the sky should be full of signals. Our galaxy should be teeming with civilizations, many of them millions, or even billions of years older than our own. We are cosmic infants. We only invented radio about a century ago. A civilization just 1 million years ahead of us would be like us compared to a Neanderthal. A civilization 1 billion years ahead would be to us like a god. The math says yes, but the sky, the data says no. This is the great silence. For decades we have been listening. We have pointed our radio telescopes at the stars searching for any signal, any beacon, any accidental leakage from another world's I Love Lucy. And we have heard nothing, only the cold empty static of the cosmos. We have looked for megastructures, giant engineering projects like a sphere built around a star to capture its energy, and we have found nothing. We see no probes, no ships, no evidence of anyone. This silence is a screaming mystery. It forces us to confront some of the most unsettling questions we can possibly ask. These questions are the great filters, the idea that there is some barrier, some impossibly difficult step between simple life and a galaxy-spanning civilization. The question is, where is that filter? Are we the first? Is the filter behind us? This is one possible answer. Perhaps the silence is here because we are the first. Perhaps the universe is not a crowded city, but an empty, silent nursery, and we are its first child. Perhaps the chain of events was so improbable, the exact right planet, the exact right moon, the spark of life itself, the leap from a single cell to complex life, the evolution of consciousness and symbolic language, that it has only happened once. Here, if this is true, the silence is not a mystery. It is a profound and terrifying responsibility. It would mean that all the hope of the cosmos, all the potential for meaning and consciousness rests on our shoulders. We are the universe's way of knowing itself, and if we fail, the universe returns to a sleep from which it may never awaken. Or is it the other darker alternative? Are we the last? Is the great filter ahead of us? This is the most disturbing thought of all. This answer suggests that civilizations do arise frequently. The galaxy has been full of life, but every single one of them, without exception, hits a wall. They all discover some technology or run into some problem that they cannot overcome, and they destroy themselves. Perhaps it is nuclear war. Perhaps it is runaway climate change. Perhaps it is a powerful artificial intelligence that sees its creators as a threat. Perhaps it is a simple matter of resource depletion. In this scenario, the Great Silence is not a nursery. It is a graveyard. The sky is quiet because everyone who came before us is dead, and we are now in our technological infancy rushing toward the very same wall that killed every single one of them. We are not the first. We are simply the next in line. There are other less terrifying possibilities. Perhaps they are hiding. In a dark and dangerous forest, you don't shout. Perhaps broadcasting your existence is cosmic suicide, and the only smart civilizations are the ones that stay perfectly quiet. Perhaps they are here, but we are simply too primitive to notice them, like an ant colony on the floor of the New York Stock Exchange, completely unaware of the complex information and intelligent life flowing all around it. But the simplest and most profound answers remain. We are either alone or we are in terrible trouble. The silence is the puzzle, and as we sit here on our tiny blue world listening to the static, we are left to wonder if we are the first to ask these questions or just the next to fail to find the answer. That great silence we spoke of is not empty. If you listen hard enough, the silence itself becomes an answer. It is filled with whispers, with ghost-like possibilities that drift in the dark. When we ask, "Where is everybody?" the universe whispers back with explanations, some of which are far more unsettling than the silence itself. We are forced to consider solutions that strike at the very heart of our own uniqueness, our future and our intelligence. First, there is perhaps the simplest and in some ways most beautiful whisper. It tells us that we are not late to the party or in danger, but that we are simply profoundly and unimaginably rare. We look at the 40 billion Earth-like worlds in our galaxy and assume they are 40 billion chances for life. But what if they are not? What if the habitable zone is a common stage but the play of life almost never begins? The leap from simple non-living chemistry, a soup of amino acids and carbon in a warm pond, to a single living self-replicating cell is a bottleneck, so narrow, so improbable that it might be the greatest filter in the cosmos. We have never been able to create life from scratch in a lab. We do not know how it happened. It may be that this spark, this transition from complex chemistry to simple biology, is a 1 in a trillion chance. It may require a perfect unique alignment of thousands of factors, the right minerals, the right moon, the right planetary core, the right star all at the right time. If this is true, the universe is not a graveyard. It is a vast, beautiful and sterile laboratory. The silence is not the sound of death, it is the sound of absence. The sky is quiet because it is empty. We are not just the first, we may be the only ones. We are the sole thinking voice in a cosmic ocean of sleeping matter, the universe's only begotten children. But there is a second darker whisper. This one says that we are not rare. It says life is common. It says intelligence is common. But it also says that wisdom is rare. This is the idea we touched on the Great Filter. This solution suggests that the path of a civilization is like a series of gates. You must pass through all of them to survive. Perhaps the jump from non-life to life is an easy gate. Perhaps the jump from simple life to complex multi-celled organisms is easy. Perhaps even the jump to intelligence is easy. But somewhere on the path there is a gate that is almost impossible to pass. And it is a gate that civilizations build for themselves. When a species becomes intelligent enough to discover physics, it discovers immense power. It discovers the energy locked inside the atom. It discovers the power to re-engineer its planet's climate. It discovers the power to rewrite its own genetic code and the power to create an intelligence greater than its own. The filter is the hypothesis that every or almost every civilization that reaches this stage fails to control its own creations. They destroy themselves. Nuclear war, runaway artificial intelligence, a bioengineered pandemic, or irreversible climate collapse. The silence in this scenario is the sound of a billion civilizations screaming and then, one by one, going quiet. The terrifying question for us is this Great Filter behind us? Did we already pass the impossible test when we evolved consciousness? Or as we sit here today with our nuclear weapons, our changing climate, and our nascent artificial intelligence, is the filter still ahead of us? Then there is a third whisper, a truly paranoid and chilling thought. It is known as the dark forest. This solution assumes the galaxy is full of intelligent life, but that it is also full of fear. Imagine the universe as a vast dark forest at night. It is filled with silent, hidden hunters. You are a hunter too. You cannot see the others, but you know they are there. What do? Do you light a fire and shout, "Here I am friendly"? Of course not. To reveal your location is to invite attack. You do not know the intentions of the other hunters. They might be peaceful, but if even one of them is hostile and technologically superior, you are instantly destroyed. In this scenario, every civilization lives by 2 rules. 1, survive. 2, destroy any other civilization you find. Not because you are evil, but because you cannot know if they are. The risk is too great. Any new civilization is a potential future threat, and the only logical move is to eliminate that threat before it can eliminate you. In this terrifying vision, the sky is silent because everyone is hiding. The only stupid civilizations are the ones like us who are naive enough to shout into the dark, sending out radio signals and probes that announce our location to the entire forest. The great silence is the sound of every other civilization holding its breath, pointing its weapons at the clearing where we are foolishly building our fire and deciding when to pull the trigger. Finally, there is a fourth whisper, one that is perhaps the most humbling of all. It suggests the universe is teeming with life. It is a vibrant, ancient and crowded city. The silence is real, but it is only our silence, because we are too primitive to understand what is happening. The life out there is so advanced, so different that we are to them utterly and completely irrelevant. Think of it this way. When you walk through a forest, you are surrounded by the intelligent and complex communication of the trees, the insects, the birds, and the bacteria. But do you stop and try to explain your political views or your understanding of calculus to an anthill? Do you even notice the anthill other than to avoid stepping on it? To a galactic-scale civilization, one that may have abandoned biology for pure energy, one that may communicate using gravitational waves or exist in dimensions we cannot perceive, we are the ants. They are not hiding from us. They are not hostile. They simply do not care. Our frantic search for radio signals is to them like listening for the sound of someone banging 2 rocks together. The great silence then is not the sound of an empty universe or a graveyard. It is the sound of a cosmic metropolis, and we are simply living in the walls, unaware of the conversation, unable to comprehend the society that functions all around us. Faced with this great silence, with these chilling whispers in the dark, humanity had a choice. We could have concluded that the silence is the final answer, turned our telescopes inward and tended to our own small garden, convinced we were either alone or doomed. But that is not our nature. Instead, we have done the opposite. We have accepted the challenge. If the old ways of searching have failed, we will invent new ones. If the simple questions have led to a dead end, we will ask more clever ones. The modern search for life is not just an evolution of the old, it is a revolution. For 50 years, the search known as SETI, the search for extraterrestrial intelligence, was defined by one thing: listening. We imagined a civilization like our own, broadcasting powerful radio signals either intentionally as a beacon or accidentally just by living. We pointed our giant radio dishes at the stars and we listened, waiting for a single unmistakable pattern, and once we thought that we heard it. In 1977, an astronomer monitoring a radio telescope detected a powerful 72-second burst of energy from the direction of the constellation Sagittarius. It was a signal so perfect, so exactly what we were looking for, that he famously circled the data printout and wrote, "Wow!" next to it. It was the wow signal, it was the ghost we were hunting, and then it was gone. We have pointed our telescopes back at that same patch of sky thousands of times. We have never heard it again. That was the old way. It was like hoping to find a single specific phone call in a world of billions, without knowing the language, the frequency, or the time of the call. The problem was not the idea, it was the scale. The sky is vast and the data is a flood. But today our greatest tool is no longer just the size of the dish. It is the mind we have built to analyze the data. We are now coupling our telescopes with advanced artificial intelligence. Instead of a human trying to guess the right frequency, we now use machine learning to sift through a torrent of data so large it is impossible for humans to check. We are teaching computers to not only look for the signals we expect, but to find anomalies, patterns that we, with our limited human imaginations, would never even think to look for. The search is no longer passive. It is an active, intelligent hunt. We have also expanded the hunt beyond just listening. What if a civilization 1 million years old has abandoned dirty and inefficient radio? What if they communicate with something far more precise like light? We are now engaged in optical SETI, pointing different kinds of telescopes at the stars to search for brief, powerful and unnatural flashes of laser light. A focused laser beam, even from a distant star, could outshine its own sun for a billionth of a second. We are looking for that impossible blip, a stellar lighthouse flashing a message across the void. And what if a truly godlike civilization doesn't want to be found? What if they are just living? How would we see them? We would look for their techno-signatures, the large-scale engineering projects they would build. The ultimate project for any civilization would be energy. Why let your home star waste 99.9% of its energy, radiating it uselessly into space? A mature civilization would surely build a way to capture it. This is the idea of a megastructure, a vast swarm of solar collectors built around the star. How would we see it? The star's light would be blocked, but all that captured energy would have to be used, and any machine is inefficient. It would produce waste heat. The structure itself would glow not in visible light, but in infrared. We are now searching the sky for stars that look strangely dim, but are surrounded by a massive unnatural glow of heat. A few years ago, we found a perfect candidate, Tabby's star, a star that was dimming and brightening in a way that was not natural. It would sometimes lose 20% of its light. While the cause is most likely a massive cloud of dust, this star was a wake-up call. It showed us that such anomalies do exist and that we can find them. We are now hunting for the unnatural, but the single greatest change, the new frontier that has redefined the entire search, has nothing to do with intelligence at all. For the first time in human history, we are no longer just looking for them. We are looking for life. Any life, even if it's just slime. We have built a new generation of telescopes like the James Webb Space Telescope that can do something that was science fiction just a decade ago. We can study the atmospheres of exoplanets' worlds orbiting other stars. When one of these planets passes in front of its star, a tiny, tiny fraction of the starlight shines through its atmosphere on its way to us. We can catch that light and split it into a rainbow, a spectrum, and in that light we can read a chemical barcode. That barcode tells us what is in the air on that distant world. We are looking for biosignatures. Think about our own planet. Our atmosphere is 21% oxygen, This is a chemical impossibility. Oxygen is a violent reactive gas. It wants to bind with rocks and rust metals. It should not be free in our atmosphere. The only reason it is because our planet is covered in life. Plants and algae are in a state of constant planetary-scale chemical warfare, endlessly pumping this waste gas into the air. If an alien astronomer looked at Earth, they would see that oxygen. They wouldn't need to see our cities. They would know we are here. That is what we are now looking for. We are sniffing the air of planets 50 or 100 light years away. If we find a rocky, wet world that is choking on oxygen, we will have found life. If we find a world with both oxygen and methane, two gases that rapidly destroy each other, we will know that both are being continuously pumped out by some kind of living biological process. This is the new search. It is no longer just listening for a phone call, it is looking for a breath. This discovery will not be a wow signal. It will be a line on a graph, and it will be the single greatest discovery in human history. For this entire journey, we have been looking out to the stars, to the galaxies, to the edge of the universe, and to the beginning of time. We have been searching the macrocosm, the world of the very large. But in the early 20th century, a group of scientists began a different journey. They journeyed inward. They began to explore the world beneath the world, the fundamental rules that govern the very small. They were not expecting what they found. What they discovered was a reality so strange, so contrary to all human intuition that it would shatter our understanding of everything. They found a world where things can be in two places at once, where particles can teleport, and where solid matter dissolves into a ghostly fog of pure chance. This is the story of that discovery, the birth of quantum mechanics. For over 200 years, our understanding of the universe was built on one solid, unshakable foundation, the physics of Isaac Newton. We call it classical physics. It was a physics of common sense. The universe in this view was a magnificent, predictable machine, like a giant clock. Everything was governed by precise laws. If you knew the position and the speed of a billiard ball, you could predict exactly where it would be in 5 seconds. If you knew the position of a planet, you could predict its orbit for 1,000 years. It was a world of certainty of cause and effect. And by the late 1800s, we thought we had just about figured it all out. All that was left was to tie up a few loose ends, but there were cracks in this perfect clockwork reality. Small annoying problems that the perfect theories just couldn't solve. The biggest and most famous of these cracks was a problem known as the ultraviolet catastrophe. It sounds dramatic, and it was. The problem was simple. Try to predict the light given off by a hot object. When a blacksmith heats a piece of iron, it glows red, then white, then blue-white. Classical physics should have been able to predict this, but when physicists applied their common sense equations, the answer they got was not just wrong, it was completely insane. The theory predicted that any hot object, a candle, a fireplace, even your own body should be blasting out an infinite amount of energy, mostly in the form of high-energy ultraviolet light. If this were true, the moment you lit a match, you would be vaporized by an infinite death ray. We knew this was wrong. We were not being vaporized, but we did not know why. The clockwork universe was broken. In 1900, a German physicist named Max Planck decided to try and fix this equation. He wasn't trying to start a revolution. He was just trying to get the math to work. He tried a desperate mathematical trick. He proposed that maybe, just maybe, energy was not smooth and continuous. We all experience energy as continuous. You can turn a dimmer switch smoothly from low to high. But Planck suggested, what if energy is not like a ramp, but like stairs? What if you can't just have any amount of energy? What if energy can only be emitted or absorbed in tiny individual packets? He called these packets quanta. You could have 1 packet or 2 or 3, but you could never ever have half a packet. It was a strange idea, and Planck himself did not fully believe it. He thought it was just a mathematical quirk. But then, a few years later, a young Albert Einstein took this idea seriously. Einstein used it to solve another problem, the photoelectric effect, where light hitting a piece of metal can knock electrons out of it. Einstein proposed that Planck's idea wasn't just a trick for hot objects. He proposed that light itself is made of these packets. Light, which for centuries everyone knew was a continuous flowing wave, also behaves as if it is a particle. He called this particle of light the photon. This was the shot that started the revolution. The world beneath the world was not smooth, it was grainy. This opened the floodgates. If light, which we thought was a wave, could act like a particle, could it be true the other way? Could a particle, like a solid tiny electron, act like a wave? The answer, proven by experiment, was a shocking yes. When scientists fired electrons' particles at a screen, They did not behave like tiny bullets. They behaved like waves. They spread out, they interfered with each other like ripples in a pond, creating a wave-like pattern. This was impossible. This was madness. How can something be a solid thing in one place and a spread-out ripple at the same time? This is wave-particle duality. At the quantum level, things are both. They are a particle and a wave, a thing and a vibration at the same time. Two men, Werner Heisenberg and Erwin Schrödinger, became the chief architects of this bizarre new reality. Heisenberg gave us the uncertainty principle. He proved mathematically that the world beneath the world is fundamentally fuzzy. You can never know everything about a quantum particle. The more precisely you measure where it is, the less precisely you can know how fast it is going. And the more you know about its speed, the less you know about its location. This is not a failure of our measuring tools. It is a fundamental law of the universe. The universe is uncertain. The clockwork machine was dead. Schrödinger gave us the master equation, the wave equation that describes how these particles behave. But what was this wave? It was the strangest thing of all. It was a wave of probability. This is the final revolutionary idea. At the fundamental level, particles do not have definite properties until we look at them. Before we measure it, an electron does not have a specific location. It exists only as a cloud of potential, a wave of probability describing all the places it might be. When we observe it, we are forcing the universe to make a choice. The wave of probability collapses, and the particle appears in one single random location. This is the world beneath the world. It is not made of tiny, solid billiard balls. It is made of pure, ghostly, probabilistic potential. Reality at its core is governed by chance. The universe is not a clock. It is a casino, and the very act of looking at the game changes the outcome. This discovery, this journey into the small, would not only change our technology forever, it would change our entire understanding of reality itself. As we journey deeper into the mechanics of the universe, the solid ground we are used to begins to dissolve. We leave the world of predictable, solid objects like baseballs and planets and enter a realm so strange that it defies our most basic common sense. This is the quantum world. The rules that govern this world are not just different, they seem impossible. Yet this is the true fabric of the reality beneath our feet. The first crack in our classical intuition is a fundamental limit to what we can even know. In our everyday world, we assume perfect knowledge is possible. If you lose your keys, you know they are somewhere. You can find their exact location, and if they were tossed, you could know their exact speed. The only thing stopping you is the quality of your measuring tools. The quantum world, however, tells us this is wrong. There is a built-in fuzziness to reality itself, a rule known as the uncertainty principle. This principle states that you cannot simultaneously know certain pairs of properties about a particle with perfect accuracy. The most famous pair is position and momentum, which is related to speed. The more precisely you measure where a particle is, the less precisely you can know where it is going. If you design an experiment to pinpoint its exact momentum, you fundamentally lose all information about its exact location. This is not a failure of our equipment. It is not because our tools are too clumsy, it is a fundamental law of nature. The very act of seeing an electron requires you to interact with it perhaps by bouncing a particle of light, a photon, off it. But an electron is so small that this bounce violently shoves it, changing its momentum. It's like trying to find the precise location of a billiard ball by slamming it with another billiard ball. The act of measuring is the act of changing. This principle, defined by a tiny but crucial number called Planck's constant, ensures that the universe at its smallest scale is a sea of probabilities, not certainties. Reality is fundamentally blurry. This fuzziness leads to an even stranger idea. If a particle doesn't have a definite position or momentum until it's measured, what does it have? The answer is one of the pillars of quantum mechanics. It exists in all possible states at once. This is called superposition. Before you look, a particle is not in place A or place B, it is in a superposition of both place A and place B. It isn't spinning up or down, it is spinning both up and down simultaneously. The particle is not a tiny ball, it is better described as a wave of potential, a mathematical description called the wave function, which describes all the places it could be. This state of all possibilities at once continues until the moment of measurement. The instant the universe looks, whether it's a scientist's detector, a photon of light, or just another atom bumping into it, the wave of potential collapses. The particle is forced to choose one single state. Out of all the maybes one is becomes reality. This is the famous mystery of quantum mechanics. The act of observation seems to be what turns quantum potential into classical reality. Before the observation, the particle is a ghost existing in multiple worlds. After the observation, it is a single solid fact. This idea is baffling, but it's the only explanation for experiments that have been repeated thousands of times. When you shoot electrons at a screen with two slits in it, a single electron travelling by itself will act as if it went through both slits at the same time, creating an interference pattern on the other side, a behaviour only a wave can produce. But if you put a detector at the slits to see which slit it goes through, the electron suddenly behaves like a particle picks one slit and the wave pattern vanishes. Reality, it seems, changes its behaviour based on whether or not it's being watched. The strangeness does not end there. It reaches its peak with a concept that Albert Einstein famously called spooky action at a distance. This is the phenomenon of quantum entanglement. It's possible to create two particles, say two photons, in a single event, linking them together in a special way. They fly apart, perhaps travelling in opposite directions at the speed of light. Let's say they are linked, so that if one is measured to be spin up, the other must be spin down. Here is the spooky part. According to superposition, neither particle has a definite spin until it is measured. They are both in a fuzzy state of up and down. Now we let these particles travel for light years. A scientist on Earth, Alice, measures her particle. It chooses to be spin up. At that exact instantaneous moment, the other particle light years away immediately chooses to be spinned out. This information, this choice, appears to travel faster than light, something Einstein's theories said was impossible. How did the second particle know what Alice did to the first Einstein thought the theory was incomplete? He argued the particles must have had hidden instructions from the start, like sending two gloves in two boxes. If you open one and find a left glove, you instantly know the other is a right glove, which isn't spooky at all. But decades of brilliant and difficult experiments have proven Einstein wrong. The universe really is spooky. The particles do not have hidden instructions. They are truly undecided until the very moment one is measured, and this measurement instantly affects its distant twin. It is as if the two particles, no matter how far apart, are not two separate things. They remain a single unified system connected by an invisible instantaneous thread. This is the ultimate nature of quantum reality. It is uncertain it exists in multiple states at once, and it is mysteriously connected across vast distances. So what is the price of all this weirdness? The price is our common sense. We must abandon the intuition we built from our everyday lives. The world of large things that we see as an illusion, and average out a large-scale symptom of this bizarre underlying reality. The solid table in front of you is mostly empty space held together by a frantic dance of probabilistic quantum fields. The reward for accepting this high cost, however, is staggering. Quantum mechanics is the most successful, most precise, and most tested scientific theory in human history. The spooky rules we just described are not philosophical speculations, they are the engineering principles behind our modern world. The laser, the transistor that powers every computer and smartphone MRI machines in hospitals, jeeps and navigation, all of these technologies function only because quantum mechanics is correct. We have a theory that works with breathtaking precision, but to use it we must give up the comforting idea that we live in a solid, predictable and local universe. We must accept that the fabric of reality is woven from uncertainty, potential and spooky connections that defy all our attempts to picture it. It is tempting to file all of this strangeness, the uncertainty, the superposition, the spooky connections under philosophy. It seems like a bizarre thought experiment, a weird story scientists tell each other. But this is not an abstract theory. It is without exaggeration the foundation of our entire modern civilization. The reason your computer, your phone and the internet exist is because we learnt to stop worrying and use the quantum weirdness. In the 20th century, we didn't just discover quantum mechanics, we learned how to engineer it. We learned to build tools that operate on the level of individual electrons and photons. The fuzziness of an electron's position wasn't just a riddle, it was a blueprint. The most important of these inventions is the transistor. A transistor is a tiny microscopic switch. It can either block an electric current to 0 or let it pass a 1. The very screen you are reading this on is powered by millions, perhaps billions of them, and a transistor only works because of quantum physics. Engineers use quantum levels, the specific allowed energy states an electron can have, to perfectly control the flow of electricity through a semiconductor material like silicon. We are quite literally commanding the fuzzy wave of potential for each electron, telling it where it is allowed to go and where it is not. Every microchip is a city built on quantum rules. The same is true for the laser. A laser is not magic. It is a machine designed to exploit a specific quantum behavior. We pump atoms with energy, pushing their electrons into a high excited energy level. Then we stimulate them to all fall down to a lower level at the exact same time. As they fall, each electron releases one particle of light, a photon. Because they all fall together, all the photons come out in perfect lockstep, the exact same color, the exact same direction, the exact same timing. This perfectly organized beam of light is what powers fiber optic internet cables, reads Blu-ray discs, and performs delicate eye surgery. Even our hospitals are built on this. An MRI magnetic resonance imaging machine is a massive quantum device. It works by manipulating the spin of protons, a purely quantum property inside the water molecules of your body. It uses a powerful magnet to align all these tiny proton spins and then flips them, with a radio wave listening for the quantum echo as they flip back. The result is a detailed map of your internal tissues, a picture drawn by quantum mechanics. These technologies are now decades old. They are the first wave. The next wave, which is just beginning, seeks to use the strangest parts of the theory, superposition and entanglement directly. This is the new frontier of quantum computing. Your classical computer works with bits. A bit is a simple switch. It is either a 0 or a 1. That's it. A quantum computer uses a qubit. A qubit, thanks to superposition, is not just 0 or 1. It can be both 0 and 1 at the same time in any combination. This one fact changes everything. If you have 2 classical bits, you have 4 possible combinations: 0, 0, 0, 1, 10, 11. Your computer must check each one at a time. If you have 2 qubits, they can exist in all 4 states simultaneously. As you add more qubits, the power explodes. A few hundred qubits linked together by entanglement could test more possibilities in a single instant than there are atoms in the known universe. This power will not be used to check your email faster. It will be used to solve problems that are impossible for any classical computer, even a supercomputer the size of a planet. Imagine designing new medicines by building a perfect virtual model of a molecule atom by atom, or discovering new materials with properties we can't even dream of, or running perfect simulations of our planet's climate. A quantum computer doesn't just calculate, it explores a vast multiverse of possibilities all at once. This new technology also brings new ways to protect information. Quantum cryptography promises truly unhackable communication. The secret lies in the uncertainty principle. The act of looking at a quantum system changes it. If Alice wants to send a secret key to Bob, she can encode it in the quantum state of single photons, for example, their spin. She sends this stream of photons to Bob. If an eavesdropper, Eve, tries to intercept the message, she is forced to measure the photons to read the key. But the moment she does, she forces the wave of potential to collapse. She fundamentally disturbs the photons. Her act of listening leaves a massive, unmissable trail of evidence. When Bob receives the key, he and Alice can check a small sample of it. If it's been disturbed, they know someone was watching. They throw the key away and send a new one. The very laws of physics become their security guard. For all this practical, world-changing power, we are still haunted by the core mystery. We can use superposition, but we still don't truly understand it. This leads us back to the most famous philosophical problem in all of physics, Schrödinger's cat. It was a thought experiment designed to show how absurd quantum theory seemed. Imagine a cat in a sealed windowless box. Inside with the cat is a tiny piece of radioactive material, a detector and a vial of poison. If a single atom decays a random quantum event, the detector senses it and smashes the vial, killing the cat. According to quantum rules, until we observe it, the atom is in a superposition. It has both decayed and not decayed. But if the atom is linked to the cat, this must mean that the cat inside the box is also in a superposition. It is at the same time both alive and dead. This is clearly impossible in our world. A cat is one thing or the other. So where does the spookiness stop? Where is the line between the fuzzy quantum world of atoms and the solid classical world of cats and people? What exactly counts as an observer? Does the detector observe the atom? Does the cat observe itself? Or does the wave of potential, the alive dead cat, only collapse when a conscious human opens the box? This is the great unanswered question. It suggests a profound and unsettling idea. The reality we see, the solid world of tables and chairs, might just be one outcome of a vast quantum probability wave. Perhaps we are not just passive observers watching the universe unfold. The theory suggests something more. By the very act of observing, measuring, and interacting, we are participating in the cosmic skekal act of turning potential into actual. We are not just looking at reality, we may be the mechanism that forces it to make a choice. For the last century, physics has been built on two colossal pillars. The first is Einstein's general relativity, the theory of the very bull. It describes gravity as a beautiful, smooth curving of space and time. It governs planets, stars, and the expansion of the entire universe. The second is quantum mechanics, the theory of the very small. It describes the fuzzy, chaotic, and probabilistic world of particles like electrons and photons. Both of these theories are perfect. In their own domains, they are the most successful and precisely tested ideas in all of human history. But there is a deep and violent conflict. They cannot both be right, at least not completely. The smooth fabric of space described by Einstein is completely incompatible with the jumpy and fuzzy world of quantum particles. The problem becomes a full-blown crisis in places where the two worlds are forced to meet places that are both incredibly small and incredibly heavy. The center of a black hole is one such place. The very first instant of the Big Bang is another. When we try to use our current laws to describe these events, the mathematics breaks. The equations from general relativity literally produce the answer infinity, a clear sign that the theory has short-circuited. The rules of quantum mechanics simply fall apart. This is not a small problem. It is the single biggest gap in our understanding of the cosmos. It tells us that our two greatest theories are just chapters in a larger, more complete book. We need a theory of everything, a single unified framework that can describe the large and the small, gravity and the quantum. The most ambitious and most famous dream of this final theory is known as string theory. The core idea of string theory is breathtakingly simple and elegant. For all of history, we have imagined that the fundamental building blocks of the universe are tiny zero-dimensional points. We call them particles like the electron or the quark. We built our entire quantum picture of reality on this idea. String theory suggests this is wrong. It claims that if you could zoom in on an electron far, far closer than any technology we have, you would not see a point. You would see a tiny one-dimensional vibrating loop of energy. It looks like a little string. This single simple object is proposed to be the one fundamental ingredient of everything. How can one thing create all the different particles we see? The answer is music. Think of a single violin string. By vibrating it in different ways, it can produce a huge variety of different musical notes. It can play a C sharp, a G, or an E flat. It is the same string, but its pattern of vibration is different for each note. String theory proposes that the universe is a cosmic symphony. A string vibrating in one specific pattern appears to us as an electron. Its vibration gives it the properties we measure, like its mass and its charge. But take that exact same string and make it vibrate in a different pattern, and it no longer looks like an electron. It now appears as a photon, a particle of light. Vibrate it another way and it becomes a quark, another way a neutrino. All the seemingly different particles and forces that make up our world are, in this view, nothing but different notes being played on the fundamental string. The entire universe, all of matter and all of energy, is just a complex orchestra of these tiny vibrating strings. This is the unification physicists have dreamed of. Instead of a zoo of dozens of different particles, there is just one thing. This idea is beautiful, but is it just a nice story? The real reason physicists became so electrified by this theory is what it did with gravity. In quantum mechanics, all forces are carried by particles, but all attempts to create a quantum theory of gravity to find the particle that carries the gravitational force, a particle they named the graviton, had failed miserably. The math always exploded into those dreaded infinities. Then came string theory. As physicists began exploring the mathematics of these vibrating strings, they found something stunning. The theory all by itself demanded the existence of a particular particle. The equations naturally predicted a particle with zero mass and a specific spin value of 2. These were the exact precise properties that physicists had long predicted for the graviton. It fell right out of the math. String theory didn't just allow for gravity, it required it. For the first time, a theory had been found that seamlessly and mathematically united the force of gravity with the quantum world of particles. The vibration of the string is the particle of gravity. It was the solution to the great conflict. But this incredible reward comes at an equally incredible cost. The mathematics of string theory is very stubborn. It is beautiful, but it only works, it only produces results that make sense. If the universe does not have the 4 dimensions, 3 of space, 1 of time that we see, the theory requires that the universe actually has 10 or 11 total dimensions. This sounds like science fiction. If this theory is true, where are these other 6 or 7 dimensions? We can move left, right, forward, backward, and up, down. We can't move shmup, shmoon. The answer provided by string theory is as strange as the problem. It proposes that the extra dimensions are everywhere, but they are compactified. This means they are curled up or rolled up into a tiny complex shape so small that we cannot and will not ever see them. The best analogy is a garden hose. From a great distance, the hose looks like a one-dimensional line. A creature on it could only move forward or backward. But as you get closer, you see that at every point on that line there is a second dimension, a tiny circle that a small ant could walk around. String theory suggests that our reality is like this. At every single point in our big 3-dimensional space, there exists a tiny multi-dimensional shape curled up smaller than an atom. These strings are vibrating within these tiny hidden dimensions. These hidden dimensions are not just a weird side effect, they are the key. The exact shape of these curled up dimensions is what dictates the laws of physics. Their geometry is what controls how the strings can vibrate. Their shape determines which notes are allowed and which are forbidden. Therefore, the shape of these hidden dimensions is what sets the mass of the electron, the charge of the quark, and the strength of gravity. The entire recipe for our universe, this theory suggests, is written in the geometry of these extra invisible dimensions. The dream of a final theory, a single equation that explains everything, now rests on this strange and beautiful idea of vibrating strings. But this idea only works if the universe has extra hidden dimensions. This leads to the most important question of all. What do these extra dimensions look like? Their shape is not just a minor detail, it is the entire format of our reality. Physicists and mathematicians believe these hidden dimensions are curled up into an incredibly complex 6 or 7-dimensional shape. This shape exists at every single point in our visible space, just as a tiny circle exists at every point along a one-dimensional garden hose. The geometry of this shape, its twists, its folds, its handles, is what determines the laws of physics. The way these dimensions are folded is what forces the vibrating strings to wiggle in specific ways. It dictates the notes that are allowed in the cosmic symphony. The precise shape of this hidden geometry is what sets the mass of the electron, the charge of the quark, the strength of gravity, and the speed of light. If this hidden shape were different, if it were folded in a slightly different way, the strings would vibrate differently and the entire universe would be unrecognizable. The laws of nature, it seems, are not fundamental. They are a consequence of a hidden geometry. As physicists explored this, a small problem emerged. By the 90s, there was not 1 but 5 different and competing versions of string theory. This was a disappointment. The theory of everything had become 5 separate theories. This confusion was resolved by a new overarching idea called M-theory. This theory proposed that the 5 string theories were not different theories at all. They were just 5 different perspectives of a single deeper 11-dimensional theory. It's like looking at a statue from the front, the back, and the side. You see different images, but it is all the same statue. M-theory is the statue. It also added a new layer of complexity. It suggested that reality was not just made of one-dimensional strings. It could also be made of 2-dimensional brains, like a sheet or membrane 3-dimensional brains, and so on. In one of its most popular versions, our entire visible universe, all the galaxies, stars, and planets is just one giant 3D brain floating in a vaster 11-dimensional space. This is where the grand symphony of ideas runs into a hard, cold wall of reality. This is the big problem. There is absolutely no evidence for any of it. String theory is so far completely untestable. The strings themselves are predicted to be the Planck length, a size so small that it is 1,000,000,000,000,000 times smaller than a single atom. To see something this small, we would need a particle accelerator not the size of a city, but the size of our entire galaxy. It is a scale that is forever beyond our reach. The theory does not, as of yet, make a single prediction about the world that we can go out and test. It does not explain any mystery we are currently measuring. Its ideas are beautiful, elegant, and mathematically consistent. But without a test, without a single piece of evidence, is it physics? Or is it just a magnificent philosophy? This problem led to an even deeper crisis. The theory was supposed to be a unique answer. We hoped that the math would point to one specific shape for the extra dimensions, the one that produces our laws, our electron mass, our strength of gravity. It did not. When physicists tried to calculate the number of possible ways to fold these extra dimensions, they did not find one answer. They found an astronomical number of possible solutions. The mathematics allows for perhaps 10 raised to the power of 501, followed by 500 zeros different stable formats or shapes. This is a number so large it is beyond all human comprehension. This is the string landscape. It is a multiverse of possibilities. Each of these 10 to the 500th power solutions would create a different universe. Each of these universes would have its own unique randomly set folded geometry, and therefore each would have its own laws of physics. In one universe, gravity might be 1,000,000 times stronger. In another, there might be no light. In yet another, electrons might be as heavy as cannonballs. Almost all of these universes would be sterile, dark, and dead. This shatters the original dream. The theory did not give us a single elegant why for our universe. Instead, it gave us a near infinite landscape of every possible universe. So, why is our universe so special? Why are the laws here so perfectly exquisitely tuned to allow for the existence of stars, planets' carbon, and ultimately us? The theory offers only one highly controversial answer. It is called the anthropic principle. This principle states that we are here simply because we are here. In a landscape with 10 to the 500th power universes, it is no surprise that a few of them, by pure random chance, would have the right laws for life to emerge. We as living, conscious beings could only have evolved in one of these rare, lucky universes. We ask, why are the laws so perfect? And the answer is, if they were not perfect, no one would be here to ask the question. To many scientists, this feels like giving up. It is an explanation that says the laws of our universe are not fundamental. They are just a cosmic accident. We did not find a deep reason for why things are the way they are. We just found out we won a lottery ticket. And so our grand journey comes to an end not with a final satisfying answer, but at the very edge of human thought where physics and philosophy are impossible to separate. We do not know if string theory is the final word or just a beautiful mathematical dead end. But whether it is right or wrong, it has left us with a new vision of reality. For thousands of years we searched for the smallest thing, the ultimate solid point that the world is made of. We thought reality was a set of tiny bits. String theory suggests there is no point. It suggests that the fundamental reality is not a thing at all. It is a pattern. It is a vibration. The universe in this final picture is not a machine made of parts, P. It is a single cosmic symphony. The fabric of reality is not made of substance, it is made of music.